Hello, Maths 1325 students. Lesson 9 is going to be on the exponential and logarithmic functions and models, and mostly these are all reviews. So you can consider it as a light topic, a perfect choice for a week after the midterm exam. Okay, here we go. Exponential and logarithmic functions. General exponential functions are defined like this: a to the x power, where the base is positive, strictly positive. Basically, this is a repeated multiplication when x is a positive integer, but we have to consider the case where x is a rational number, even an irrational number. When x is a rational number, this expression is algebraic. That is, it can be written as a repetition of addition, subtraction, multiplication, division, and some radicals. When x belongs to a whole number, that is 0, 1, 2, 3, 4, and so on, then this is nothing but a repeated multiplication of x times. When x is 0, then I'm multiplying nothing 0 times, so a to the 0 power is 1. So 1 times repeated multiplication of x, and x is 0, so no multiplication at all, so 0 power is 1. Now if you have 1 power, then multiply a once, so that's a. Second power, then multiply twice, so a times a. Third power, then is a times a times a, like that. Now what if you have a negative integer? That's going to be a repeated division, or a reciprocal of repeated multiplication. Either way, you can see it like that. Now, what if x is a rational number? In that case, it's going to be defined as a radical like this. A to the n power is going to be either repeated multiplication or repeated division, and then take the nth root of it. You know, the inside is always positive because a is positive, so you don't really have to worry about some negative number inside any radical. And here is a visualization. So here we have a to the x power, where x is not all rational, that's too much, so just n over 20, where n is running from negative 100 to positive 100. So let's see, this is basically, let's see, negative 50 to positive 50, and then the increment is 1 over 20, so it's going to be 0.05, that's the increment. And then we have a bunch of dots. And then this program is randomized, so if I run it again, I'm going to get a little bit different shape. See the difference? Oh, this time a is less than 1, so repeated multiplication will make things smaller. So we have decrease. Now, what if we fill those up? Because you see, we have rational numbers only, but overwhelming majority is irrational, so we'll be able to fill those up. If we do, then you're going to get a smooth curve. And that is the general exponential function, where x is a real number. In that case, we get these kind of graphs. Here's some examples. 3/2 to the x power, so 1.5 to the x power, that's blue, and then 2 to the x power, that's red, and 3 to the x power, that's green. Of course, I could have thought of many other examples, but then again, 3 examples like these are going to be sufficient. You see, a is all greater than 1, so repeated multiplication will make things bigger, bigger, bigger. So as I move to the right, the graph is all going up. Graphs are all going up. Now, repeated multiplication of 1.5 versus repeated multiplication of 2, which is bigger? 2 is bigger, so repeatedly multiplying 2 will make it grow quicker. So for the same x-coordinate value, red is above blue. And 3 is even bigger, so green is above red. If I had 10 to the x power, then that'll grow even quickly. And then if we have say 1.1 to the x power, is going to grow even slower. Now what if this a is less than 1? we get this kind of graph. 2/3 to the x power is blue, 1/2 to the x power is red, 1/3 to the x power is green. And then repeating the multiplication of a less than 1. So as I repeat it, the value is getting smaller, 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 and that's what we are looking at. Oh, by the way, they all share the same y-intercept because 0 power is always 1. You see, 0 power is always 1. Now, let's graph these two together. So here, 2/3 to the x power blue, 2 to the x power red, and 3 to the x power green. And look at these. 2/3 to the x power blue, 1/2 to the x power red, 1/3 to the x power, and look at the symmetry. If you take all these and then flip those with respect to the y-axis, and that's what we have over here, and vice versa. And then please note that all these are reciprocals. 3/2 becoming 2/3, 2/1 becoming 1/2, 3/1 becoming 1/3. They're all reciprocals. Actually, they are related like this. Reciprocals, so make those into negative x power, negative x power, negative x power. Now we have the same base, and then x is becoming negative x. So it's a flipping with respect to the y-axis. Either way, we get these properties. Domain is negative infinity to positive infinity. Let's look at all those again. Horizontally, it can be anything. Range is positive numbers only, 0 to infinity. No graph goes down, 0 or higher, but nothing reaches actual 0 because you see, no matter how many times you multiply by 2/3 or 1/2 or 1/3, you never actually get 0. Divide by half. No matter how many times you do that, it stays positive. It just gets closer and closer and closer to 0, but never actually touch 0. So strictly greater than 0 to infinity. So that's the range. And the y-intercepts are all 1. We talked about it already. A to the 0 power means repeated multiplication of 0 times. So no multiplication at all to 1. So stays at 1. In an exceptional case, 1 to the x power, we have constantly 1. Okay, just constantly 1. That's an exceptional case. Those are general exponential functions. I hope everybody remembers all those. Now let's consider some special exponential function, e to the x power, where e is defined kind of like this expression, limit of 1 plus 1 over n to the nth power as n goes to infinity. It's basically 1 plus 0 to the infinity power expression. Or like this, 1 over 0 factorial. 0 factorial is 1, not 0. 1 over 1 factorial, 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, and so on. Add them all up, and magically we end up with the same number, 2.718, something like that. And if you set that particular number e as your base, then it turns out that we have this kind of graph, and the slope of tangent line at the y-intercept happens to be 1. That exponential function is called a natural exponential function, or the exponential function. And this number e is often called Euler number. And it is called e, actually, it must be coming from exponential, not Euler. Sorry about that. Anyway, that's a natural exponential function. And that is the most important type of exponential function there is. And of course, here you learned some calculus already, so let me tell you a little bit more. You see, the slope of tangent line is 1. That means the derivative is 1. Derivative evaluated x equal to 0 is 1. And that's why the natural exponential function is simpler than other exponential function. You see, 1 is simpler than other positive real numbers, in terms of computation, of course. This feature was not really emphasized in algebra classes, but This is calculus, so you should know that. That's very, very important feature. And that's why natural exponentials are more important than any other exponential functions. Let's see, do we have some time for logarithmic functions? Let's try. General logarithmic function is basically the inverse function of exponential function. So a to the x power is the original function, and it'll turn out that it is just strict increasing function. Oh, not just it'll turn out. Let me just show you the graph. Yeah, like this. Increasing, so they're all one-to-one functions. Or decreasing, they're all one-to-one functions. So they are invertible, so inverse function exists, and that's the logarithmic function. So all the properties of logarithms apply. Domain becomes range, and range becomes domain. And then if you compose inverse of original, or original of inverse, then you get cancellation. F inverse and F cancel out, and we get x back. So log a of a to the x power is just x, cancellation. A to the log a of x, cancellation, we get x back. So basically we can do it like this. So these cancel out, those cancel out, we just get x. Likewise, these two collide and cancel each other out. These two cancel each other out, and we just get x. It's a cancellation basically. Original and inverse, or inverse and original, they cancel each other out. And then one more thing, anything to the 0 power is 1, and because of that, log of 1 is 0. You see, you can write this 1, which I'm highlighting in red, as a to the 0 power, and then we can apply the cancellation rule. Log of a and then exponential by a kill each other, and then we get original power back, so 0. So log of 1 is 0. And then we have this kind of graph. You see, all the exponential function crosses 0, 1, y-intercept 1. And then, just like any inverse function, symmetric with respect to the diagonal, x equals to 1. So logarithmic function is going to 1, 0 here. And that's for all. I mean, this program is randomized, so if you run it again, you get a little bit different exponential and logarithmic function, but the y-intercept, x-intercept, they're the same. And then same symmetry. And the reason we have symmetry is, of course, that's what the inverse functions do. X going to y and y coming back to x. And that happens to be the very same dynamics of folding over. For this paper, along this diagonal, then x-axis is right going on top of y-axis and vice versa. So x is going to y is going to x. That's basically what inverse functions are doing. That's why we have this symmetry. And then, in this case, we have decreasing when a is less than 1, but we'll never consider anything like this, so never mind about these kind of graphs. Instead, let's focus upon the natural logarithmic function, and of course, e is that same e. The Euler number, 2.718, and so on and so forth. And then that's the natural exponential function, and take the inverse of it, and that's a natural logarithmic function. So log base e of x, or ln of x. Some people just write it log of x. I like to do that personally, but our textbook author doesn't do that. Our textbook author always uses ln, and I'll follow that. And then here's a graph of the natural exponential function and natural logarithmic function. Right here at x equals to 0, y equals to 1, there we have slope 1. And that is the slope of tangent line there. Right over here, again, slope 1. That's the slope of tangent line there. Those are the features. I hope everybody remembers all those. We'll talk about the exponent rules and logarithmic rules in the next video.